All right. So then, okay, yes, ROLSES. This name is a follow-up to earlier missions we had that were called ROLS back in the days of well, previous work for Lunar paper. Anyway,
Sorry, Bob. Could you speak up? I can barely hear you.
Okay, yes, I'll try to be louder. Hopefully my system works for this. If yell again if you can't hear me. Radio observations of the lunar surface photoElectron sheath is ROLSES. The primary goal is to determine the photoelectron sheath density of a few meters above the lunar surface. And this has some scientific value for a variety of reasons. And there are also several other goals, which is what we are going to discuss in the next few minutes. So, as indicated, the co-Is are William Farrell of Goddard and Damon Bradley of Goddard. The frequency range that we cover is the low band of 10 kilohertz. Well, there are two frequency bands, but the low frequency is 10 kilohertz and the high frequency is 30 megahertz. We only get down 17 kilobits per second of data. We hope to have 4 stacer antennas, which are suggested here on this old version of the Intuitive Machines Nova C lander, 1, 2, 3, 4. And let's see, next slide. So regarding the lunar surface photoelectron sheath, of course, there's been a lot of analysis of these things and simulations have been done. And there are a few measurements that are relevant, but not as much detail as ROLSES will provide if everything works right. Here, this figure on this page is from a paper by Farrell et al. And they did calculations using a simulation for various types of solar wind, the standard, post interplanetary shock, flare related, CME related. And so we're not going to be measuring at 30 meter heights. We're just going to be measuring at 1 millimeter and 3 millimeters. But you see that there is a variation there. So that is what we hope to detect, is something that corresponds to this simulation or other, and compared to other simulations, which give slightly different results. So that's the first goal. A second goal we have is that we would like to demonstrate the detection of other sources of radio emissions from observatories on the lunar surface. Here is data from the WIN spacecraft, and it's in a similar frequency range. And you see terrestrial auroral kilometric radiation. You see a solar type 3 radio burst there. You see emission from Jupiter, and ROLSES should see these things. In addition to, well, at this point, wind is at solar Earth L1, so it's farther than the moon. So the radio frequency interference from Earth is not as intense as it is at the lunar surface, which will be addressed in a moment. So this plot is a 24-hour interval covering the frequency range for the WindWave spacecraft, and we'll have on the order of 13 plots like that from ROLSES if everything works the way it should. We may also detect dust impacts, interplanetary. I'm not talking about the lunar dust, but interplanetary dust or interstellar dust coming down on the lunar surface in spacecraft flying through those dust particles. The contact of the dust on the spacecraft body or on the antenna causes a change in the photoelectron environment, which really releases electrons and ions, and depending on the magnetic field, it takes time for things to return so that the signal changes. And so here at the plot at the right is a Cassini detection of a Saturn ring. So as it goes through the ring and the dust particles strike the spacecraft, you see this electric signal. So ROLSES might detect dust impacting the Nova C lander or our stacer antennas. Our time resolution of 4 seconds would only permit us to detect dust clouds. It's not designed to detect individual dust particle impacts. Another thing that we might be able to do is, of course, there is no ground plane below the Nova Sea lander or the ROLSES antennas, and detected radio waves will, likely penetrate the lunar surface and go to some depth. And it's possible, depending on what is down there, that they might be reflected and redetected. So, just as an example, let's just say in a moment we'll look at some terrestrial RFI. Maybe there will be a blast of terrestrial RFI, which goes past the antennas and then comes back after reflection. And then in a situation similar to the Apollo 17 lunar surface electric properties instrument that made measurements of where the signal generator that sent radio waves down to into the lunar deep into the moon, maybe up to a few kilometers. And this paper in Icarus there is described a recent analysis of the solar electrical properties instrument results. And for example, they said because no deep interference were detected, the thickness of the volcanic fill must exceed 1.6 kilograms and possibly reach 3 kilograms. So maybe something will happen that will allow us to make a couple of comments about the lunar surface below, or the features below the Intuitive Machines Nova Sea lander. And then a technical aspect of the measurements are that we should measure the terrestrial radio frequency interference reaching the near side of the moon. And ROLSES will provide continuous spectra, which will probably include this. As a comparison, here is a plot from the WindWave spacecraft at a time when it flew very close to the moon, passing the moon. And as you can see, over 24 hours, it was at a time when the solar wind, the solar activity was low. So the type, come back cursor, thank you cursor. These vertical lines are solar type 3 radio bursts. They're rather weak because of the interval in the solar activity. On the other hand, the horizontal lines are radio transmissions escaping from the Earth and coming to the moon. And so we expect to see quite a bit of that. And a key question is how much more terrestrial radio frequency interference is there. It's relevant because there are some discussions about putting in a radio observatory on the near side to study radio emissions from the terrestrial magnetosphere, but it will be contaminated by the terrestrial RFI. So this is a measurement that is important to make. And just to to wrap things up here, just to show you a view of a Nova Sea lander with ROLSES components on it. There is our main electronics box here with a radiator, a sheet of metal above it to reduce its temperature, which gets quite high because of being on the lunar surface. And if you're at noontime, well, for example, you can see at the top of the lander, which is a solar array, gets up to about 120 degrees Celsius. We use radiators on each of the components. That is our main electronics box and our 4 preamp boxes to keep the temperatures of the electrical components below 60 degrees Celsius. And the assumption here is that the lunar surface at noon at this latitude is 108 degrees Celsius. So, in summary, there is one thing here that's keeping me busy. ROLSES is not an engineering model or flight spare, so we are to a certain extent building a new instrument. We're using the main electronics board is something from a previous Goddard instrument called JEDI, which is an instrument now on the International Space Station. So the schedule for the components is that they should be everything will be assembled by the end of May. It's a complicated payload compared to many other NASA-provided or LSITP lunar payloads because we have 4 stator antenna units, 4 front-end preamplifier boxes, and a major electronics box for the data collection and transfer, and of course harnesses to collect to connect all of these units. Oh, let's see what has happened. I'm not sure why my MacBook has just done that. I guess the MacBook. Can you still hear me? No.
Yes, it just says it's the end of the slideshow.
The MacBook decided that it was done. Anyway, we will finish testing the final version, and the current plan is to ship it to Intuitive Machines by the end of September 2020. Thank you. Any questions?
All right, thank you. We have time for one quick question. And if there is not one, we will move on to try to regain some of our time here. Thank you for sticking on time. That was great.